Very good day. I would like to meet Dr. Samsud. I'm Sham, daughter of Ramlu with matrix number 207823. I'm from group 4. Our group members consist of 4 members: myself, Nor Akila Uzma binti Nor Hisam, Muhammad Hafiz Aiman bin Abdul Rahman, and also Poshwalian. And the title given for our group is the production of 100 kilotons of polybutadiene from 1-butane. So the objective of our project is to design a chemical plant that is capable of producing 100 kilotons of polybutadiene with 98% of purity per year from raw materials of oxygen and 1-butane. And throughout this project, we use several raw materials, catalysts, and solvent as listed in this slide. For the raw materials, we used oxygen and 1-butane. For the catalyst, we used molybdenum-based catalyst and also benzene catalyst. And for solvent, we used hexane and also furfural. So for the summary of the overall plant, this plant consists of 10 main units, which are 7 main units and also 3 auxiliaries. For the main units, we used reactor, water separator, oxygen separator, extraction column, distillation column, polymerization reactor, and also hexane separation unit. While for the auxiliaries, we used 2 compressors and 1 cooler. So this is the overall process flow diagram of our polybutadiene manufacturing plant. Now I'll proceed with the main chemical reactions with the respective units. The first unit is reactor, which functions to convert butane into butadiene. So the reactor that we used is a fluidized bed reactor that uses oxidative dehydrogenation method of N-butane, and this method uses pure oxygen and there is no side reaction detected. As for the chemical equation, the butane reacts with oxygen to produce butadiene and also water. We used the fluidized bed reactor because it is an excellent reactor type for highly exothermic process, and this reactor also offers significantly higher efficiency in terms of heat exchange, temperature control, as well as rapid circulation. And as for the operating condition, this reactor operates at the temperature of 679 degrees Celsius with a pressure of 16 bar, and it yields 0.85. The next unit is separator, which intends to remove water. The water is removed prior entering the second phase separator. As the bottom effluent of phase separator is solely water without any contaminants, the water is then sent into water storage tank for another usage. And the operating condition for this water separator unit is 20 degrees Celsius and 5 bar, and the efficiency is 100%. The next unit is another separator, but this separator functions to remove oxygen. The top product is fed to another phase separator, which separates butadiene and excess oxygen, and the excess oxygen is discarded as gas. And the operating condition for this separator unit is 66 degrees Celsius and 5 bar. This unit also functions at an efficiency of 100%. The subsequent unit is an extraction column. This is to extract 1-butane from the vapor liquid mixture, and the assumption that we used is that all raffinate and extract are in equilibrium. Their composition must lie on the phase envelope and must be connected by a tie line. The fluid remains in the extraction column long enough for equilibrium to be achieved, and the operating condition of this extraction column is 180 degrees Celsius and 8 bar, and the mass extract is 0.97 of 1-butane. The subsequent unit is the distillation column, which functions to separate a mixture of butadiene and furfural by condensation. At the top of the distillation column, the vapor reaches a condenser, which cools the vapor, and the condensation process separates the furfural from the vapor phase. And the operating condition of this distillation column is 300 degrees Celsius and 9 bar, and the assumption that we used is approximately 0.99999 furfural is recycled. The next unit is a polymerization reactor, which functions to polymerize butadiene into polybutadiene with the presence of organic solvent hexane and also benzene catalyst. And the last, and for the operating conditions of that polymerization reactor, it operates at the temperature of 100 degrees Celsius and a pressure of 1500 bar. The solvent that we used is hexane, and the catalyst is benzene catalyst, which with an efficiency of 486 kg of polymer produced per mole of catalyst used. The selectivity of this unit is 0.947, and the amount of solvent needed is for 1 mole of butadiene, 0.831 mole of hexane solvent is needed. And for the last unit, it's a separator which intends to separate hexane solvent from the polybutadiene. And this unit operates at a condition of 300 degrees Celsius temperature and 9 bar of pressure. And the polybutadiene purity that is obtained is 0.98. That's all from me. I'll pass to the next presenter.
Assalamualaikum warahmatullahi wabarakatuh. So next we are going to bring about material properties. So the main raw material that we use is 1-butane, butadiene, polybutadiene, and also furfural. So 1-butane, it has chemical formula of C4H8 with the colorless gas and also gasoline-like odor, and also with a density of 620 kg per meter cube. For butadiene, it has chemical formula of C4H6 with colorless gas and also has mildly aromatic odor with a 615 kg per meter cube. So for polybutadiene, it has chemical formula of C4H6 with N, and also its color is black with low odor, and also density of 1,120 kg per meter cube. Lastly, we have furfural, which is, it has chemical formula C5H4O2 with colorless oil and also smells like almond-like odor with a density of 1,160.1 kg per meter cube. So next, we have 1-butane have a melting point of negative 185.3 degrees Celsius with a negative 6.47 boiling point degrees Celsius and also negative 79 degrees Celsius of flash point with a vapor pressure of 1,648 mmHg with the molar mass 56.108 gram per mole. 1-butane also soluble in alcohol, ether, and also benzene. For butadiene, it has negative 108.9 degrees Celsius melting point. It also has boiling point of negative 4.49 degrees Celsius, flash point of negative 5 degrees Celsius, and also vapor pressure at 25 degrees Celsius, which is 2,100 mmHg. Butadiene has molar mass of 54.0916 gram per mole. Butadiene also has soluble in water and also alcohol. So next we have polybutadiene. It has negative 6 melting point, which is it also has 9 boiling point, and it has flash point of 260 degrees Celsius. Vapor pressure at 1,840 mmHg with a molar mass 54.09 gram per mole, which is slightly similar with butadiene. So polybutadiene also soluble as aliphatic hydrocarbon soluble. So lastly, we have furfural, which is it has melting point of negative 37 degrees Celsius with a 162 degrees Celsius of boiling point with a flash point of 62 degrees Celsius. It also have vapor pressure at 25 degrees Celsius, which is 2 mmHg. It has molar mass of 96.085 gram per mole. Furfural is soluble in ethanol, ether, acetone, chloroform, and also benzene. So next, we have flammability. So 1-butane, it is extremely flammable. Gas or air mixture are explosive. It also has exposure limits between 1.6 to 10%. The prevention for 1-butane is no open flames, no sparks, and no smoking. It must be in the closed system, ventilation, explosion-proof electrical equipment, and lighting. So next, we have butadiene. It also extremely flammable. Gas or air mixture are explosive. It also has exposure limits between 2 to 20%, which is slightly higher than 1-butane. It also must have no open flames, no sparks, no smoking, and it must in the closed system, ventilation, explosion-proof electrical equipment, and lighting. Prevent build-up of electrostatic charges if it in a liquid state. So for polybutadiene, this substance is non-hazardous and non-toxic. It has no detrimental effect on the human body, so it also has no exposure limits. So lastly, for furfural, it is flammable. Above 60 degrees Celsius, explosive vapor or admixture may be formed. So its exposure limit is in between 2.1 to 19.3 degrees Celsius. So the prevention for furfural is no open flames, no sparks, and no smoking. Above 60 degrees Celsius, must use a closed system, ventilation, and explosion-proof electrical equipment. So next, I'm going to present about the equipment list that we have in this process. So there are 10 units with 7 main units. First one is a fluidized bed reactor with the element tag number R101. Its function is to convert one butane to butadiene with a temperature of 679 degrees Celsius with 16 bar. Next, we also have cooler with element tag number E101. Its function is to reduce the temperature of a mixture after the reactor. So its design temperature is 20 degrees Celsius and also the design pressure is 4.88 bar. So next we have separator. Separator, we have three types of separator, which is first one is S101. Its function is to remove water from the mixture with a temperature of 20 degrees Celsius and also 5 bar. Next we have S102, which is its function is to remove oxygen from the mixture. Its design temperature is 66 degrees Celsius and also 5 bar. Lastly, we have S103. Its function is to separate hexane solvent from polybutadiene, this is the final unit in our process. So its design temperature is 300 degrees Celsius and also the design pressure is 9 bar. Next, we have compressor. Compressor, we have two compressor, which is C101 and C102. C101 is to increase the pressure of one butane and butadiene with a temperature and pressure 138 degrees Celsius and 6 bar. Next, we have C102, which is to increase the pressure of butadiene and furfural, which is its design temperature is 247 degrees Celsius and also 9 bar. Next, we have extraction column. In element tag number T101, its function is to extract one butane from the vapor liquid mixture with the desired temperature 180 degrees Celsius and also 8 bar. Next, we have distillation column with T102 tag number. Its function is to separate a mixture of butadiene and furfural by condensation. Its temperature is quite high, which is 200 degrees Celsius, and also design pressure with 9 bar. Lastly, we have polymerization reactor, which is crucial for our process with the R102 element tag number. Its function is to polymerize butadiene into polybutadiene with the presence of organic solvent hexane and benign catalyst with a temperature of 300 degrees Celsius and also 9 bar. So that's all from me. I will pass the floor to Po Julian. Thank you.
Now, let's move on into comparison between Excel and Aspen simulation. First, for the reactor. So, as we can see here, for reactor 1, there are no significant difference between the values for mole flow rate, the mass flow rate, and the operating condition. However, the phase inside the stream is different between Excel and Aspen, as this might be due to the assumption made by our group mate. So, as we can see here, this is gas, gas, and gas. Meanwhile, for the Aspen simulation, the phase is liquid, vapor, and vapor. So right here we can see the difference between the mass flow rate and mole flow rate. It is not significant difference, and it can be ignored. Next, moving into the extraction column. So for extraction column, there are significant differences between the values of all components. Supposedly, only one butane was pushed fully through stream 11 as shown in Excel calculation. However, using Aspen Plus, only half of it was pushed along with small amount of butadiene and furfural. The outlet temperature is also different, which can be the main cause to a lower extraction efficiency of the column in Aspen Plus. A more detailed calculation on the design and especially the condition used in this column is needed to get a higher extraction of butadiene in both Excel and Aspen Plus simulation. So, according to the explanation, we can see that the temperature is different, so it makes the extraction column in Aspen Plus has less efficiency right here. So next is for the distillation column. The distillation column was made to separate butadiene from its solvent, which is furfural. Both Excel and Aspen give high amount of butadiene in our product stream 11. However, the amount of furfural recycled was a bit different, where there are only 7.86 kmol/hour furfural being recycled. Similar to the extraction column, more details on the design and the operating condition is needed to obtain a high efficiency of the separation process. Right here this is the significant difference between them, between the Excel and Aspen. Next, lastly, polymerization reactor. Due to the assumption made during the manual calculation in Excel, there are significant difference on the flow rate between Excel and Aspen simulation in the polymerization reactor. This is because in Aspen simulation, we are using a more detailed calculation for the reaction occurring inside the reactor. This is what this means is like for the Aspen, we are using different method and different ways to make sure that we can get the result, which is really complicated and hard because we never learned about the method before. Meanwhile, the Excel calculation only using basic knowledge on the material balance, since there is a complicated reaction occurring here. However, both calculations still manage to get high amount of polybutadiene with high purity. So in conclusion, the result shown for Excel and S1 Plus is different due to the lack of information on the unit that we are using. To further improve our calculation and result, we should do more research about the units and the component that we are using. Moreover, it is also logical that our result will differ because Aspen Plus uses more data and information to calculate the result compared to Excel. That's all from my part. Thank you.
Now I will talk about the pollution control. First, I will talking about the Sustainable Development Goals SDG 9 to convert and concord a reliable control system. Second, SDG 12 to be responsible for the consumption and production with proper management. Third, SDG 13 to sustain the environment from hazardous gases and pollutants. Fourth, SDG 14 to preserve the aquatic life and living organisms from harmful pollutants. Fifth, SDG 15 to protect human life, flora and fauna from harmful pollutants. Next, I will talk about the safety analysis. For the material hazards is flammable, toxic, explosive, less severe hazards, environmental hazards, and health hazards. For the precaution measure, wear proper PPE, avoid breathing gas or vapor, keep away from heat, spark, open flames, and other ignition sources, and dispose of content and containers in accordance with all local, regional, national, and international regulations. For the conclusion, the objective for this project has been successfully achieved. The design process has been simulated using the Aspen Plus software and Microsoft Excel. The simulation results show that Aspen Plus modeling is more powerful and robust compared to calculation methods. Pollution control and waste management were also discussed to assess possible methods of handling the push gas from the production plants. Last, all possible hazards associated with the chemical components and equipment used in the manufacturing process were identified. For the recommendations, first, construct the manufacturing plants near to the raw material supplier. Prepare a cost estimation to evaluate the feasibility of the design project in terms of economic aspect. Explore alternative waste management approach that can market the usable products. Employ heat exchanger in the plant design for cooling and heating purpose to save utility costs, and apply hazard study to all the process units accessible in the production line to have a more comprehensive and reliable safety analysis and risk assessment of the production plants. This is the reference for all of our projects, and that's all from us. Thank you.